Good morning, everybody. So today we're going to discuss the main issues with regard to welding repair of dragline buckets in the mining industry. So mainly dragline buckets are used in the mines to remove the ore burden from the earth. So they are mainly, and the topic today will be the dragline buckets. So this is the bucket that's used to remove the ore, dump it from one side to another. So these buckets frequently encounter failures, and since the bucket is made out of steel, the primary welding process of the primary means of metal joining is welding. And the welding processes that are commonly used for repairing of dragline buckets are shielded metal arc welding, which is mainly used in on-site repairs. And then we have gas metal arc welding, which is mainly used for in-shop repairs. And then we have flux core arc welding, which is a superior process, but is mainly used only by original equipment manufacturers and not in mining sites. And lastly, we have robotic welding, but this is mainly avoided due to the high cost of procuring the robots and also the setup time. So it's more feasible only in large-scale mass manufacturing and not suitable for repairs. So now let's look into some of the key reasons of the failures in dragline buckets. So the main failure, based on all the research studies and literature review that has been done, the main failure caused by dragline buckets is due to fatigue cracks in the welded joints. Now we need to understand why these fatigue cracks occur in the first place. So they occur because of the high frequency of stress events during operations. So this leads to a lower number of cycles to failure than intended. So the stress is mainly in the welding joints due to the tensile residual stresses that are acting at the heat affected zone. And also it can be due to delayed hydrogen cracking and embrittlement. So see, these are some of the major issues of failures in weld joints. And there could be other reasons as well. Wear could be one more reason, because the metal is quite abrasive, and this causes abrasioness of the plate, and then it could eventually lead to wear and failure of the bucket. So some of the most commonly used methods employed for failure mitigation are the removal of compressive residual stresses on the welded joint are the use of low hydrogen consumables. So this is during the use that is used during welding. Also the optimizing the heat input selections during welding. Post-weld heat treatment. This is one of the very most commonly used method for removing the stresses. So the post-weld, the joint is heated to a very high degree, depending upon the joint type, to free the metal from all the weld metal from all the stresses. Peening is one more process, and also grinding, which is employed. But all these processes are very time consuming. It requires extra labor, extra effort, and this means that the bucket is not in the field, which reduces its reliability and downtime, which is not ideal. So one of the promising modern things that we have right now is the use of something called as LTT consumables, or low transformation temperature consumables. So what do these consumables do is, in comparison to conventional consumables, they boost the fatigue strength of the welded joints without the need for any post-welding afterwork application. So that's one of the key benefits of using an LTT consumables. Now, how does low transformation consumables work? So at a material or metallurgy level, it mainly exploits the phase transformation of the weld beads during the cooling process. And it relaxes the tensile residual stresses caused by the weld. So compared in standard filler materials, they're either magnetic or ferritic, depending upon the strength level. But LTT consumables produce a weld that are primarily composed of martensite, with a martensite start temperature of usually 180 degrees centigrade. So mainly it takes advantages of this phase transformation temperature at 180 to 200. Mostly it's around that temperature, and it gives a rapid cooling, which makes the joint more robust and with high fatigue strength, thereby increasing the life of the joint. Nickel and chromium are the most commonly used alloying elements in LTT. Earlier studies were done in the Soviet Union in the 1960s. And then I think it was more formalized around 1999 by Ota et al., who had carried out studies first using 10% of nickel and 10% of chromium. So with regard to this research question for this will be the application of, there are a lot of studies being done in this area, but either studies have been done only the use of conventional filler materials or only the use of LTT filler materials. But there have not been any studies done using a combination of both LTT as well as conventional filler materials. So the research question here was to see how will this combination work? Because LTT consumables, one thing is very costly, and secondly, they are not very frequently available. So that would limit its use. So having a combination of both would, in a kind of way, give a best of both in terms of economics as well as in terms of getting a good, robust joint. So the research design, what we took was an experimental approach. We used 2 structural steel samples of both the structural steels S355J2 and S960QL. Iron, chromium, nickel-based filler material was chosen for this experiment in conjunction with commercial filler materials of magnesium and G4Si1 for joining this. And the welding process used for the experiment was gas metal arc welding, and samples were produced both in butt weld and filler weld configuration. After the weld, post-weld heat treatment, there's no heat treatment, I'm sorry. So after the weld, fatigue testing was carried out using a constant amplitude sinusoidal tensile wave in the longitudinal direction for filler welds and in the transverse direction for butt welds. And the testing was done in a frequency range of 29 to 40 Hz at a stress ratio of 0.1. So the results obtained during this test were butt welds showed a 40% higher fatigue strength at 2 million cycles than welds that were made from conventional filler materials. And in filler welds, we saw a 34% improvement in comparison to conventional welds. Also, it was observed that weld metals with martensite transformation temperature was close to about 190-200 degrees centigrade, which gives the best fatigue strength. So in conclusion, we can say that a combination use of both conventional as well as LTT filler materials. So the first pass could be conventional, and the final pass, because given that the dragline buckets are thick, they would obviously need multi-pass welds. So maybe the initial welds could be of conventional filler materials, and the final pass could be of LTT filler materials. And I think this would give the best joint with the best fatigue strength at the best cost. Thank you. That's it from me.